Hello, good evening students of class 12. Today let us learn about the last topic of this chapter, that is the energy stored in a capacitor. I am Dhanusaria. Please watch the video till the end so that this concept of energy stored in a capacitor is understood by you. Capacitor stores electrical energy in the electric field between the plates. So we will understand what is the formula of the energy stored and how this happens. Okay, so now as you can see, we have a capacitor with two plates. Let us consider both the plates, that is both the conductors in the beginning are uncharged. Plates. And then we slowly start charging it bit by bit such that we are transferring charge from the conductor 2 to the conductor 1. We are transferring a positive charge. So next we charge the plates. How do we charge the plates? By transferring positive charge from conductor 2 to conductor 1. This is the way we are transferring the charge. Fine. And in this process of transferring positive charge from the conductor 2 to the conductor 1, we have to do external work. So what do we have to do? We have to do an external work. Why? Because at any point, why? Because at any point of this charging process, the plate 1 will be at higher potential compared to the plate 2 at lower potential, as can be seen. Positive means higher potential, negative means lower potential. So at any point of time or at any stage of charging, the plate 1 will be at a higher potential compared to the plate 2. Now, in this process, let us consider an intermediate stage where the plate 1 is having, let me write this intermediate stage. What is this intermediate stage? That the plate 1 is having a charge of Q dash and the plate 2 is having a charge of negative Q dash. What is our aim? Our aim is to set up a charge of Q on the plate 1 and charge of negative Q on the plate 2 such that we form a parallel plate capacitor with opposite charge plates. Fine. This is our aim. So we are on our way to finish this aim. And in that intermediate stage, let us consider of transferring a small infinitesimal charge delta Q dash from 2 to 1, plate 2 to the plate 1, such that plate 1 now has Q dash plus delta Q dash. Okay, so in this intermediate stage, we have started transferring how much charge? Delta Q dash, said that the plate 1 has now the charge of Q dash, already it had, and let it have delta Q dash. Fine. So in this intermediate stage, let us consider the potential difference between the plates as V dash is equal to Q dash on C. Okay, V dash is equal to Q dash upon C, where C is the capacitance of the system. Fine. Okay, so we are transferring delta Q dash from conductor 2 to the conductor 1, and we have a potential difference of V dash is equal to Q dash by C. So we are doing a work. How much work? Let us find out. Fine? And our final stage which we want is this stage, where Q and minus Q are the charges of the plate. Intermediate stage is this one, where we have Q dash and negative Q dash. We are taking charge of positive delta Q dash from 2 to 1 conductor. Fine? Okay. So now let us calculate the small work done in transferring the small charge delta Q dash from plate 2 to the plate 1. Fine? So the external work required to shift this charge of delta Q dash of this delta Q dash is given by delta W is equal to V dash delta Q dash. Work done is equal to VQ. That's what is written here. Okay. So let me substitute V dash as Q dash upon C delta Q dash. Fine. Now this is a small work done to shift delta Q dash from the plate 2 to the plate 1 in this intermediate state. To get the total work done, we have to integrate on both the sides from 0 to Q. So we get integral delta W, integral 0 to Q, Q dash upon C delta Q dash. We have W is equal to 1 upon C. Let us take it outside from here because C is a constant. Integral 0 to Q, get integral Q dash upon C delta Q dash. Fine. And integral of delta W is written as W, the total work, the total external work. Fine. So using the formula of integration x raised to n dx integral is equal to x raised to power plus 1 upon power plus 1. We have W is equal to 1 upon C. Power is 1 here. So Q dash square power plus 1, 1 plus 1 upon 1 plus 1, that is 2. And we apply the lower limit 0, upper limit Q. Therefore, we have W is equal to 1 upon C, Q square upon 2. If I apply 0, the answer will be 0. Fine. Okay, so upper limit gives me this, which amounts to shuffling or rewriting it as half Q square on C upon C, or simply we can write Q square upon 2C. However is convenient to you, you shall write down the formula of work done, which is stored in the capacitor as potential energy. So this is equal to U is equal to Q square upon 2C is the potential energy stored in the capacitor. Now here you can write or substitute Q is equal to CV such that you get U is equal to C square V square on 2C, where CC cancels out, so we get half CV square. That is another equation. Fine. You can also substitute C is equal to Q by V in this original equation or here also. Fine. So U is equal to, let me substitute here. C is equal to Q upon V such that we get half Q upon V multiplied by V square. Again V cancel, we get half Q V. Okay, so here you can see there are three equations for U, 1, 2 and 3, that is a potential energy stored. We can write them all together as U is equal to Q square upon 2C is equal to half CV square is equal to half QV. As the numerical is given to you, accordingly you can use any of these formulas for the energy stored in a capacitor. Fine. Okay. So I hope the process of finding the value of energy stored in a capacitor is understood by you. And we have reached from this intermediate state to this final state of the capacitor. You can consider that the energy which is stored in this electric field between the plates. Fine. And when the capacitor gets discharged, this energy is released. Okay. When the capacitor gets discharged, this is the amount of energy released in the discharge. So this is the discharge energy released also. Fine. Okay. So I hope this concept is understood by you very clearly. I shall just move and you take a pick. In the next page, we shall understand different forms of this energy when we consider the capacitance depending on the shape and size, that is A and D. Okay. So keep watching till the end, and at present take a pick of what we have derived just now. So continuing the previous stage, we have learned that the energy stored in the capacitor is having the formula U is equal to half Q square upon C. Other conversions also we have discussed, but let us consider this conversion at present. Where is this energy stored? This energy is stored in the electric field between the plates of a capacitor. Fine. And when there is a discharge of the capacitor, this energy is released from the electric field. Okay. Now, to understand the energy density, let us rewrite this energy, potential energy again, and consider that we substitute surface charge density as Q by A such that Q is equal to sigma A. We substitute Q is equal to sigma A here such that we get U is equal to half sigma A whole square, and let us also substitute C is equal to A epsilon naught upon D in the denominator so that we get A epsilon naught upon D, which I write it here as D. Fine. Okay. Then in this situation, let us multiply and divide the numerator and denominator by epsilon naught such that we get sigma square A square upon A epsilon naught. Epsilon naught I multiply up, D I write, and epsilon naught I write down also, so that I get epsilon naught square. And I cancel A and A here. So, okay. Now here we get half sigma square A epsilon naught D upon epsilon naught square. But we have already learned in this chapter that this is all we have learned, which I am just jotting down here. Fine, that E between the plates, which is seen here, is equal to sigma upon epsilon naught. Therefore, E square is equal to sigma square upon epsilon naught square. So here I have sigma square upon epsilon naught square. So we substitute E square instead of that. We also know that AD is equal to volume of the capacitor. So we write it as volume V. Okay. So we can write here AD together also at volume. Now let us see how we can write this equation as U is equal to half. This I substitute as E square mentioned there. AD I write it as volume. What is left out? Up epsilon naught. So I can rewrite this equation as U potential energy or energy stored in the capacitor upon volume, bringing volume down there, okay, is equal to half epsilon naught E square, which is the energy per volume, which is called as energy density, denoted as small u. This is capital U, this is small u. So energy per volume is energy density. What is this? Energy stored per volume, which is energy density, small u, given as half epsilon naught E square. So finally, we wanted energy density, small u is equal to half epsilon naught E square, which we have found out just now, and I mentioned it here. Fine. So what is energy density of electric field in a capacitor? It is energy stored in the capacitor per unit volume, which is given as small u in alphabet is equal to half epsilon naught E square. Fine. Okay. Now half is a constant. Epsilon naught is also a constant. Permittivity of free space. So here you can have energy density U directly proportional to E square. This also you remember. Fine. Okay. So in this particular video, we have learned so many formulas of the energy stored in a capacitor. So let us write all these formulas one by one in the next page for a quick revision. Fine. At present, take a pic of what we had derived just now. Okay. And keep watching the video such that we go to the next page to write quick formulas to remember for your JEE NEET preparation. Fine. Now we make a quick formula page for remembrance and revision for the entrances like JEE and NEET for the energy stored in a capacitor. First one, U is equal to half Q square upon C. Second one, U is equal to half CV square. Third one is U is equal to half QV. Fine. Okay. Then let us go to the energy stored for a parallel plate capacitor with the dimensions A as the area and D as the distance between them. So that becomes U is equal to half epsilon naught E square, which where E is the electric field between the plates, A the area of the plate, D is the distance between them. Then AD can be considered as a volume, so we can write the energy density as U, small u, is equal to capital U upon volume, which is equal to half epsilon naught E square. From here, we can also write U, that is energy density, directly proportional to E square. This will be again used when we talk about the magnetic energy stored in an inductor. This is electrical energy stored in a capacitor. Fine. Okay. So take a pick, understand these formulas as a quick revision and use these formulas according to what is given to you in the question. So these formulas must be in your mind ready at any time. Fine. Okay. So I move here. You take a pick of what we have written just now.